thank you so much for coming to my talk. I'm really excited for this one. This is my first time giving this talk, so you all are my pilot audience. We're going to be doing a roundup, right, isn't that appropriate for Texas, of observability data stores or databases or whatever you want to call them, right, where you put your stuff. So first of all, I want to thank you all for coming here and actually caring about this. This is a quote from a talk at ApacheCon in the Cassandra track. And I think it's accurate, right? Like most developers don't actually care how their database works or what's going on with the bits and the bytes. They just want to shove them somewhere and be done with it. So you're here, you're special. You do ask questions like this. You do care about this. Or if you don't, now's your chance to leave. All right, who am I? My name's Josh. I am an open source advocate at a company called Altinity. We do open source hosting and support for a database called ClickHouse, which you're going to hear me talk about more. One point of clarification, we are not the maintainers of ClickHouse. ClickHouse Incorporated is. We're not affiliated with them. We are just open source contributors. Our lawyers made me say that. OK, so before this, though, I was a product manager at an observability platform, and that is where a lot of my opinions about observability come from. So to start with some of my opinions, right? Here we have a picture of a cockpit on an airplane from like the 1970s, 80s, right? This is an older model airplane. I think an airplane is a great metaphor for modern distributed systems and also observability, right? We need all of these different systems with different pressures and interactions working with each other in tandem. We need to monitor the health of all of these systems sort of through these analog tools that then maybe eventually get translated to something a little more akin to digital. And we need lots and lots of levers and buttons, right, to put control inputs back into the system to keep it behaving the way that we want it to behave. So this is great. We had all of this, right? We had all of this figured out in aviation and in our world in software. This is a more modern cockpit, right? So here we have a 787, beautiful airplane. If you ever get a chance to fly in one, it's one of my favorites. One thing to notice, there's still lots of buttons and dials. That's for a really good reason specific to aviation. Boeing tried to make a cockpit that was all touchscreens, and pilots hated it because touchscreens are very difficult to use in turbulence. But all of the dials are gone, right? All those dials and gauges, gone. They've been replaced with these 4 general purpose screens that can show the pilots exactly what they need to see in any given moment. And to me, that is the cornerstone of observability. It's context, right? So here's my definition of observability. It's visibility and understanding, right? And that understanding comes from that context. So this is a really, really simple definition, but there's a lot to it, right? We need to be able to see everything that's happening within the system. We can't like go add another instrument to the airplane wing while we're flying, and we don't really want to like re-instrument our production applications while they're running. So we need to make sure that there's enough data coming out that we can already see everything that we need to see. And I think the talk after mine will talk about some of the methods that you can use to do that. Thanks, Steve. And then can we understand it, right? Can we make sense of what we're looking at and understand why it's doing what it's doing and what we need to change in order to get it to do something else? There is a challenge here in this, right? So this is just a rule of thumb that I use. Like any rule of thumb, it's going to vary based on your specific use case, but it's that for any given application that you're building, your observability data will be like 2 to 3 orders of magnitude greater than the data that's actually part of the system, right? That's part of the application. So we have this massive, massive volume of data that we need to put somewhere so that we can actually do useful things with it. So what is that data actually, right? What is in there? Well, we have, of course, our telemetry signals themselves. Usually that's going to be metrics, traces, and logs. There are some newer ones that you might have as well, or we might call these things wide events. But right, we have our telemetry events. Then traditionally we would have like labels and tags, which is just a way to like sort and find those telemetry signals based on who cares about them or what system we're trying to examine, right? In the modern open telemetry world, we would call those labels and tags resource metadata. So now instead of just labels and tags, we have this map of key value pairs. This is actually really, really useful information that I think is often not given due credit for how important it is, because as an engineer building a system, right, like I don't care about logs or metrics or traces. I care about containers and pods and processes and VMs, right? These are the things that I actually can identify as being something that I or my team owns on an enterprise. And so the resource metadata is actually a really, really useful way to tie all of this information together and filter it if we can keep its richness. Once we have all of that data, right, especially if we're using something like distributed tracing, we can start to build out dependency graphs and topologies of our system. This becomes another useful way to filter and sort the information and find the information that we specifically care about. Once we've got these graphs and topologies, right, calculating those can be expensive, so maybe we want to store some snapshots and deltas and save on that CPU and compute so that we don't have to recalculate it every time we're running a query. And then these snapshots and deltas can also be used to speed up other queries. And then finally, right, you're going to have just your basic configuration stuff like dashboards and alerts and users and permissions. So what do we need in our observability database? Well, first of all, we need really, really fast ingest, right? If your ingestion slows down, best case scenario, you're just going to lose some observability data, which is preferable. You would prefer to just not record the data. Worst case scenario is you'll actually bring your production system down because it was unable to export the data to your telemetry backend. That's really bad. Try to avoid that, but I have seen it happen. Then, right, we need fast multi-row analytics. We need to be able to aggregate over sometimes millions of rows in order to calculate averages, P99s, P90s, right, things like that. So we need to be able to do math really, really fast across all of our signals. Sometimes, especially if we're dealing with logs, right, full text search can be really, really useful to find the specific logs that we care about. Or if we have really, really good tags or labels, or we're using those resource metadata appropriately, right, we can use that as our search mechanism. It's a little bit less computationally intense and easier to build indexes around. So on the note of right, the multi-row analytics, this is just another definition that I really like. Anything you can do with a group by, that's what analytics is. So we're starting to get into like more databasey stuff, right? And this is going to get a little bit more technical as we go. So some more requirements for observability, right? We need efficient compression and storage because, as I mentioned, it's going to be 50 times larger or more than our actual data. So it would be great if we didn't have to pay, through the nose to store all of that. Observability data is almost always time-oriented, right? Like we care about specific windows in time. We're using time as a way to correlate across different systems. And we're going to have some kind of retention period at the end of which we don't care about our data anymore, and we want to be able to quickly throw away all of the old data. So having time-oriented management is very important. Often, for a lot of observability use cases, right, we need to be able to read the last data point, and that's actually the only thing we care about, right? Like think about alerting. All we're doing is reading the last data point across a range of time series, and then trying to create an alert if that last data point falls outside of a certain range. And then most databases, right, we think about like post and put operations, like we have this idea of an update. But in observability, do we really need updates? I would argue maybe we don't, because the data is pretty much write once, read many, right? You're going to write it once. You never really need to update it. You can just kind of append new data. So with databases that are architected for updates, we're actually kind of slowing ourselves down when it comes to observability. So, okay, I'm going pretty fast. I'm going to slow down, take a breath, take a sip of water. All right. Yeah. Yeah. So we've got our ground level set. Now let's dive into the nitty-gritty a little bit. So we have our different database archetypes, right? OLTP is what you're probably all familiar with, right? So transactional processing database. This would be like MySQL or Postgres or most of the traditional databases that we would think of when we're building an application. Online transaction processing. And then we have OLAP, or online analytics processing, which is sort of another style of database that lends itself more to these multi-row analytics types of use cases. Then we have TSDB, which stands for time series database. So Prometheus would be, of course, the most famous of these, but there are others. And then we have, like, I didn't have an acronym for this, but like search or analytics or combination search analytics databases, which tend to all sort of be around the Lucene family, which I'll talk about in a little bit. So, like I mentioned some of these already, but here's the cast of characters that we're going to be talking about today. There are a lot more databases that I didn't have time for. A lot of them will kind of fall into one of these categories also, or share some similarities between some of these, right? So we have Postgres, which is a traditional transactional database. We have Cassandra, which is kind of a more scalable transactional database. We have OpenSearch or Elasticsearch, which there was a great talk in the slot before about using that as an observability backend. Very, very common use case for it. And then Prometheus is just, as Dave has said, the de facto standard for metrics. So that's a very important one to look at. And then finally, my personal favorite, I am biased, ClickHouse, which is sort of an example of an online analytics processing database. Taxonomies are challenging. All of these databases right? Like, I wanted to organize this talk based neatly on those categories and kind of go through them one by one, but you can't really. Because what's been happening for the last decade or longer is that all of these databases have been borrowing tricks from each other. So they kind of have all started to blend together and start to look the same. So I kind of made this, like, this is just my opinion of, like, kind of where they all fit into a taxonomy, but it's very, very blurry. Okay, we're going to talk about storage on disk, right? So now I'm going to talk about some of the architectural tricks that we can use for databases, and then at the very end, we'll talk about which databases use what and what you should use them for. The disk is always going to be the slowest part of your database. That's just never going to change. That's always where the latency comes from. And if you can avoid reading data off of the disk, you can speed up your database processing dramatically. So how we store the data on the disk is actually going to be really, really important. There are a couple different styles for how we can look at this. Heap pages, this is the most common. This is going to be like how Postgres does it. We're going to have time series database blocks, which are append-only structure. And then we also have immutable parts or segments, which are used by a couple of the database engines that we're going to look at. Excuse me. So heap pages, I like to, since we're kind of at like a hardware adjacent conference, right? It's kind of like the JBOD of storage styles. It's like, JBOD stands for just a box of disks or just a bag of disks, right? It's like a RAID, but not quite a RAID. So heap pages just insert the latest page wherever it fits on your disk. Just fill up the disk. And then when you delete stuff, right, you have to come around and like remove some of those pages, and then that creates new space for new pages that might get inserted. But you don't really care too much about where the data goes because you're going to keep a bunch of indexes that help you find it really quickly wherever it is. Time series database blocks, as I mentioned, are append-only. So this lends itself a little bit more to this observability use case of writing really, really fast and often, but never doing updates, right? And so in a time series database, you would have a TSDB file for every unique time series, and you're just adding the last sample to the end of that file. Which is useful for ingestion, is also useful for reading, because if we only care about one time series, all the data is just laid out right there for us to read sequentially, which is really, really nice. And then we have our immutable parts and segments with background compaction, right? So that's sort of what separates these from the TSDB, which is append-only. Now we're dealing with immutable files that then get merged into larger files in the background, which is another way of increasing the efficiency of your queries, right? So kind of see we have like a batch insert that would create a new part, and then there's some kind of process in the background that's ordering that data and merging it into larger parts, which can create a lot of disk I/O, right? So like this is a computationally expensive trick, but it also leads to really, really fast databases. Okay, so we've got our storage mechanisms. Now, how do we actually write the data into the database, right? This is an important part. A lot of this comes down to like what kind of guarantees do we want to give? What kind of fault tolerance do we want to have? A write-ahead log or a commit log, there's lots of different words for this, but like whatever you call it, basically a very common trick is to just kind of have this log of all of the inserts that is then being pulled from to actually lay the, like the data doesn't get laid out in the formats that we were just talking about, it just gets written to the commit log or the write-ahead log, and then there's a process that is organizing that data into the correct format for the database. And this gives you nice fault tolerance. If there's ever a delay and that data didn't get organized or something, the server got rebooted, you can go look at the write-ahead log and see what wasn't actually committed yet. So that's nice. We also need some way of dealing with concurrency, right? Especially if we care about updates or deletes, and we have multiple processes, and one process is reading the database, and another process is writing to the database at the same time, and they're both looking at the same rows. We need some way of dealing with those discrepancies. So there is the multi-view concurrency control is one strategy. And this basically is like having a snapshot of your index is a good way to think of this. So like if the index points to the file, then that file is part of the database at that snapshot. And when you do a write, you create a new copy of the whole index and point to you copy the row that you were writing and point to that row in your new index. Meanwhile, any processes that we're reading can use the previous snapshot and have a consistent view. Then what we need to do is do some, like I mentioned, we have to go back and clean up any of those older records that are no longer pointed to by any snapshots. That process is called vacuuming. Tombstone deleting is another method of handling deletes and updates, right? We can basically just continue to write to append only or immutable files, and then mark which ones should be deleted, and then the query engine can check that tombstone list and go, oh, I'm going to ignore those files even though they were part of my query because they have been deleted. And then another strategy we have for concurrency control is simply last write wins. Just put a timestamp on everything, and if you get 2 of the same thing, use the latest one. So that's a pretty simple strategy. One more trick we have for, I mentioned indexes quite a few times, right? So balance trees, everyone here I'm sure is familiar with balance trees. They look like this. This is really, really commonly used for the indexes inside many of these databases because it gives us a nice tree graph that we can traverse and quickly find the key value pair that points to the blocks that we care about. With those tricks that we have just been over, we can build ourselves a Postgres. So a Postgres database uses a write-ahead log. It uses heap pages and multi-view concurrency control, and it uses balance tree indexes. Cool, right? So why don't we just all use Postgres for everything? Well, actually, Postgres, you can kind of just use it for everything, and it's not a terrible idea, and we'll talk more about that why later. But it's optimized for updates and upserts and row-level reads, right? So this is the typical transactional workflow. It gives you really strong asset guarantees, which is really important if we're doing things like transactions, right? Like actual financial transactions or anything where we need, to guarantee that all of the updates that are part of a transaction have happened before the whole thing is committed. And because of those guarantees, scaling it horizontally can be a little bit challenging, right? There's not a lot of like distribution possibilities when you're dealing with things this way, and you need these really strong guarantees. So at scale, that's kind of a reason to not use Postgres for observability. So we have other architectures that lend themselves more to observability. This is the category that I'm going to call analytics and search, and it's a very, very broad category involving many, many databases. But sort of the first trick that we have in this space is what's called log-structured merge tree. So this is a way of ordering the data on the disk, and this graph comes from Ben's blog post. I highly recommend reading his blogs and looking at his talks. He explains this stuff way better than I could. So a log-structured merge tree, right? We basically have data coming in as key-valued pairs, buffered in memory, and then sorted, and then flushed to disk periodically. And then again, like I mentioned, that background compaction, so these parts that were written to disk in the background get merged into larger and larger parts, again, maintaining that sorting that's going to be really, really important for speeding up our queries. We'll talk about that in a little bit. Log-structured merge tree is most popularly implemented by the Lucene engine. So if you're not familiar with Lucene, you've actually probably used it, even though you didn't realize you were using it. Lucene is the underlying engine for Cassandra, Elastic or OpenSearch, Apache Solr, and a bunch of others. And actually also a lot of observability vendors are using the Lucene libraries inside their product to power search, even if they're not necessarily using one of these databases. So it's a really, really popular project that not enough people have heard of, but it's awesome. It's really oriented around search. So here's what a Lucene query looks like. So this is what I mean when I say, like, you've probably used this before inside an observability product. Cassandra is an awesome Lucene-based database, right? So Cassandra kind of takes that Postgres architecture that we were looking at, and instead of just using the heap pages, now adds immutable parts so that we can optimize these queries a little bit more for faster ingestion and faster reads at the expense of some background processing. It makes it a little bit more scalable than Postgres as well. It still maintains some of those row-level guarantees, and it's still storing data in a row-oriented format, which is important. And so Cassandra is awesome, and it scales better than Postgres, but it's not the most scalable thing for observability, and you will eventually hit hard limits if you try to use it for massive enterprise observability workloads. Then we get into vector engines and search, right? So these basically take the architecture of Cassandra and add some special sauce on top that make it really, really fast to find specific blocks, to find specific data that you care about. Those tricks are inverted indexes, Bloom filters, approximate nearest neighbor. There are a bunch more, but these are sort of the 3 main ones, and you can kind of combine these in really intelligent ways to create really, really fast query engines for search. So inverted indexes, if you haven't seen them, it's basically just like, right, traditionally an index would be like a key that points to some data, and an inverted index is just the reverse. We're taking one of the words or keywords or pieces of content from the data, and using that as the index, and it points to all of the actual primary keys that hold that word. So we can think of, right, like you can see how useful this would be if we were trying to create a literal search engine. We can actually make them even faster, and that's what Bloom filters do. So Bloom filters give us not necessarily a yes or no answer of if a piece of data is in a specific block, but basically what you do is you hash the data in that inverted index and do some clever math with the hashing so that you can tell with absolute certainty that a specific word does not appear in a specific block, right? So you basically get from a Bloom filter all the blocks that you can skip for a specific query, which, as I mentioned, if you can skip reading some stuff off of the disk, things are going to be a lot faster. So this is really awesome. And then, sparse indexes snuck in there. They weren't on my list, but let's talk about sparse indexes really fast. So sparse indexes, kind of the opposite, right? We can think of those Bloom filter and invert indexes as being really, really dense. They contain lots and lots of keys. Like you're gonna end up with lots of index rows, basically, for all of your data rows. Sparse index is the opposite. Say we have a long list of rows ordered on time. We can have a sparse index that just says, hey, this whole block starts at 2025, 01, 01, whatever, and ends at 2025, 01, 02, whatever, right? So it's basically like a very light index that can help us very quickly and easily find a large block of ordered data. And then approximate nearest neighbor. So this is a trick where in the inverted index, we were looking at literals, like the word dog, which is nice, but like that's not a semantic search engine, and semantic search engines can be really, really useful. Semantic search engines operate on a data type called a vector, right? And these vectors are kind of these mathematical things that can't necessarily be easily, like they don't have a direct correlation to each other, but we can place them in a multi-dimensional space and calculate how close they are to each other. And once we have calculated that closeness, we can then build a graph of nearest neighbors, and we can use that graph to traverse and find the specific block that we care about. So by combining this with inverted indexes and Bloom filters, we can build a really, really powerful semantic search engine. Okay, then we get into something a little bit more purpose-built, right? Like I say Prometheus and friends because there's like 12 different Prometheus or PromQL compatible databases. Some of them follow the Prometheus architecture, some of them have their own architectural tricks. This talk isn't long enough to go into all of them, but we're gonna talk about Prometheus, right? So as we saw before, it uses this append-only structure where you're just adding data to the end of a time series database file. This is really, really awesome, especially if we just need that last sample, right, for alerting. But it has a challenge. Who here has heard of cardinality explosion or has encountered a cardinality explosion? Yes, so that comes from this little formula right here, right? Basically, for Prometheus, you're gonna end up with one of these TSDB files for every unique combination of labels. That means you have to care about what you put in your labels. Like, you have to think really, really hard about if it's worth adding a new label. Thank you, thank you. Yes, exactly. So like throw your IP addresses in your labels and just blow up your Prometheus instance or your Datadog bill. So here's kind of a graph visualization of cardinality explosion, right? This is like a small one, right? So be very, very careful when using Prometheus specifically and thinking about what labels you put into it. But there is something really, really nice about this structure still, right? And that's that it's column-oriented. So all of the metrics, all of the measurements that we care about for a specific query are already sitting next to each other on the disk. That's really nice because it lets us do math on them really, really fast, right? So we can think about it like this. In a traditional row-oriented database like Postgres or Cassandra, we're reading all of the columns in a row, and that's how the data is actually laid out on the disk, which is nice if we need to read the whole row, but bad if we need to do analytics on an entire column. And then columnar orientation also gives us one other benefit, which is more efficient compression, right? In a column, every value is going to be the same data type, which means we can much more easily compress it. And we can do clever things like delta encoding, which then reduce the size of the data even further. So when we talk about efficient compression for observability, columnar orientation is extremely important. Here's a nice visualization to kind of demonstrate that, right? So say we have a table, 59 gigabytes, just arbitrary size, right? 109 columns. This is a pretty typical table. If we wanted to read if we wanted to read 3 columns in a row-oriented database, we would actually need to scan all 59 gigabytes off of the disk. And however long that takes, that's how long this query will take to start. Once we shift that data into column-oriented, we reduce that down to 3%, right? We only need to read 1.7 gigabytes off of the disk. That's way better. And then if we compress the data, which we can do because it's in that columnar format, we get down to, what is that, 0.035%, right? So like now we're talking about less than 1%. And then we can also multi-thread this because the data is immutable. So if we do that over 8 threads, we're down to less than 0.5%. So we can do this query way faster with columnar data. And this brings us to ClickHouse, which kind of combines that column-oriented thing with the immutable merging blocks thing. And what you get is something that looks kind of like this. So whereas with Lucene, we had immutable parts containing key value pairs, with ClickHouse, we have immutable parts containing columns, right? That's the big difference here. And just like with Lucene, right, as those parts get merged into larger and larger parts, our queries get faster and faster, and we get longer and longer columns of data that we can read immediately and do math with. So this is pretty awesome, right? Okay, Victoria Metrics gets my first honorable mention of all the databases that I haven't mentioned yet. It kind of combines some of that time series database stuff that's especially efficient for that last sample read with some of this like stuff that ClickHouse had incorporated with merge tree and background compaction. So Victoria Metrics stores 1 file per day is how it organizes its parts and kind of gives you not all of the benefits of both of these, but a lot of the benefits of both of these. So if you really just care about metrics, I think it's a great choice. Other honorable mentions. There are so many observability databases that did not make it into this talk, but all of them are awesome. Loki in particular, we use that in our cloud. It's awesome. It's a dead simple tool, right? Like if you just want something that just works, Loki's great. Cortex and Thanos are on the CSCF. Those are Prometheus compatible databases. Mimir from Grafana is also Prometheus compatible. Timescale DB is an extension for Postgres that teaches Postgres some of these observability tricks, right, to make it much faster for metrics specifically. Apache Solr, kind of you can think of that as an alternative to Cassandra, and it could be used for logs. And then Druid, which if you have a lakehouse, you could look at. It's pretty cool. So, all right, which one should we use for what? This is the last section of the talk, and then we'll have some time for questions. So I show this graph often, and usually when I'm talking about OpenTelemetry, right? Not when I'm talking about databases, and then people come up to me and they're like, oh, Josh, should I use these databases? Well, yes, actually. These are great choices, especially if you only care about only one of these signals, right? Like if you only care about metrics, then Prometheus is an awesome choice. If you only care about traces or you're building a trace-based observability tool, then ClickHouse is a great choice. And if you just have a ton of logs that you want to be efficiently stored and you want to be able to efficiently search, then Elasticsearch or OpenSearch is a great choice. So, okay, but it's a little more nuanced than that, right? Like I can't just give one answer for what you should use because this is a very complex problem. So at a very, very small scale, I'm a huge fan of not introducing new tools until you need to. So just use what you already have until it breaks. Maybe you can use one of those Postgres extensions and throw your data in there until you get too big for that. If you're really, really hooked on full text search, I don't think there's any better choice than OpenSearch or Elasticsearch. They're just kind of dominant in that space, right? If you want just one database that can do everything and you only have one thing to manage, then I think ClickHouse is pretty cool. I've given a talk about this called All-in-One that you can look up. If you want to do wide event analytics, ClickHouse was purpose-built for this. It's awesome for this use case. So if you just have wide events and you want to do analytics on them, I would say choose ClickHouse. If you need to do heavy, heavy filtering before you analyze your wide events, then OpenSearch becomes a good choice again. It's very, very well optimized for this. And if you're just trying to do alerting or lots of last sample reads or time series dashboards, then you should probably choose something that's purpose-built for that. You're going to end up storing a lot less data. You're throwing away a lot of the richness in your data by like reducing all of that cardinality and those labels, but you're going to get something that's going to work very, very efficiently for this use case. And if you need wide event analytics With transactional guarantees, which is not really an observability use case, but I think it's just kind of cool to think about, you could use Cassandra. That's probably most commonly where Cassandra is used. But you could also just use Postgres for your transactions and then use something like a sync connector to dump all of your data into something like ClickHouse or Druid and use that to run your analytics. And that's actually a really, really common architectural pattern that we see. So if you have non-observability data that you want to combine with your observability data, that might be a way that you can do it. All right, so in summary, right, we've got Postgres, which is a transactional database that is SQL compatible. I didn't talk too much about query languages, but there are different query language flavors, and they're listed here. The storage for Postgres is heap pages. It uses balanced tree indexes primarily, although it has other tricks. And it's best for if you need updates or upserts with guarantees. Cassandra, similarly, OLTP, SQL. We're now using Lucene engine under the hood, and we're making heavy use of inverted indexes to quickly identify the Lucene segments that we care about. And it's really, really good for scalable upserts where you don't want that ingest to slow down. You want it to just keep going. Prometheus, right, it's using the time series database format that we talked about. It uses PromQL, which of course is extremely popular. Tons of tools support it. And the indexes are by label, right? So the labels on your metrics time series is how you're able to find them. Loki, which I didn't mention, also is kind of architecturally similar to Prometheus in that it is storing the logs in an append-only structure, and then it does not provide any kind of like full-text search, or it does, but you have to scan the whole database because it's not storing it in an index. But for your labels, those are all indexed, and that's how you can really, really quickly find your logs with Loki. OpenSearch, again, we're back to Lucene engine under the hood. OpenSearch directly exposes the Lucene query language as its primary query language. And it's got a whole bunch of indexing tricks that it uses to make your searches faster. And then finally, right, ClickHouse is our analytics processing database. It uses the merge tree engine. It has other engines, like there's a replacing merge tree engine that you can actually use to do updates and upserts using that last right win strategy that I mentioned. Out of the box, ClickHouse uses mostly sparse indexes to identify the parts that you'd care about, but it also can support inverted indexes and Bloom filters if you want to use those for things like, say, an OpenTelemetry resource attributes map field, right? And it is useful for wide event analytics. That went a little faster than I thought, but we have now, I think, 10 minutes for questions, so thank you so much. Yes.
I really like your general, maybe Postgres is fine. Yesterday, Thursday, I learned that Postgres can do the inverted index things.
Yep.
You can give it a bunch of text, and it will tell you where the words appear.
Mm-hmm.
And it's just in there.
Yep.
Yeah,
yep.
Nice.
And there's PromQL extensions for Postgres and for ClickHouse. And there's, yeah. So like all of these databases are kind of starting to blur together. And if you're already using Postgres, then like, use what you got. Yeah. That'll be the title of my talk next time I give. Postgres is amazing until ... I'm not familiar with those two databases. Yeah, okay. Okay, I'm going to have to look into this more.
Yeah, so there's databases that just are built around vectors. And so it'll have all that plugged in, plus everything you said. So take a look at Milibus. It's made by China, so be careful with that one. It's kind of a piece of crap. But we found HugeRant, who was, their competitor, right when it was early.
are these open source?
Yeah, QDrant is open source, Milvus is open source, it's Kubernetes.
Okay.
QDrant also has a service to where you can easily just go send stuff.
Yeah, they have a managed cloud.
Super base style, communication with your application. But yeah, no, I wanted to know if you had done anything, built anything with that in the stack at all.
No, I'm more on the ClickHouse side, so a lot of the stuff outside of ClickHouse here for me was new research.
Oh, okay. Okay, cool. Right
Yeah.
on. All right, thank you.
So a ClickHouse question. What's the relationship with ClickHouse and Apache Parquet?
Great question. Thank you for asking it. So ClickHouse natively has an S3 integration that is sort of good for importing and exporting data from S3, and like Parquet is a columnar format that would really commonly be used to keep columnar data on S3. ClickHouse Cloud, right, the company that I mentioned at the beginning, has a proprietary S3 integration that uses specifically AWS S3 as primary storage, but it is not included in open source ClickHouse. In April, my company launched what we're calling Project Antalya. It is what I would call a production-ready beta. We're still very much building it out, but we have many customers using the read path in production. And what Project Antalya is fully open source integration between ClickHouse and object storage as primary storage, using Iceberg as the database table catalog format and Parquet as the storage format for now. The nice thing about this is you can write all of this data, right? Like the end goal for Project Antalya is that you can write your data to a ClickHouse instance, have that merge tree engine be merging the parts on your really, really fast NVMe drives, and then once those parts have gotten big and are kind of old, they can get TTL'd off to your S3, where you can keep them for as long as you want because it's so cheap, and they can still be part of the same queries without the person, right? Like it's part of the schema, so the person writing the query doesn't actually have to care where the data lives because it just got moved to where it was most efficient. Yeah?
I've got a dumb question.
No dumb questions.
What's the difference between a trace and log?
That's a good question. That's a really good question. Really, it's there's not much difference, right? They're both wide events, and if you can relate a log to the previous log that like triggered it, you have a trace.
Trace is a lot like a stack trace.
Yeah, that's formatted, right?
Yeah. It like shows you a certain method.
Yeah.
A log is like I did a thing, but
Yeah.
it's like
But
you can mush
a
the
trace
thing
is
and do the
just
same.
a trace is just a formatted log to which we've all agreed to what the format is going to be and includes a request ID that we can track.
Yeah. Bingo.
It's literally what we did when we put it together under open census.
Oh, nice.
So
Makes sense.
Yeah.
No, I just used a path from Prometheus to Grafana.
Yep.
So I connected to Kubernetes.
Yep.
I use Hubble, Cilium, Prometheus, Grafana.
Awesome
So
tools.
it's kind of all seamless. I think you said Postgres can be used. So I was wondering, is there easy connectivity from, say, especially for tracking metrics, say from Postgres to Grafana? Is that even like?
Yeah, I believe there is a Postgres connector for Grafana, but for Cilium data, I would probably not use Postgres.
I'm just curious because it took me some time to get it connected. But then I'm like saying, oh, well, Postgres could be used for small deployments, is what I'm doing.
Yeah.
So then the question becomes, is Grafana, is it like kind of savvy enough to say, I can still take the time series metrics from Postgres?
Yeah, that's going to depend on the specific Grafana extension or data source that you're using. So basically, the data sources will run the query against whatever database you have. There are two data sources for ClickHouse. My company maintains one of them, right? And so part of the trick is just taking that data and getting it into the exact table shape that Grafana expects for its visualizations, which is like the time series is the first column, then you have all the labels, and then you have all the measurements.
Right. So I can easily lay out all my panels and graphs and all that on Grafana and just say, just point to Prometheus and show me this metric.
Yeah. So Prometheus is a lot easier because PromQL is kind of purpose-built to spit out the right format. With SQL, you're going to have to use something like SQL using Postgres. You would have to use window functions, and your queries are going to look a little bit more gnarly, but you will also have a lot more flexibility because you have all of that rich metadata.
Okay. Sorry, that answers my question.
Okay.
There has to be some catch.
Yeah.
I can do PromQL.
Yeah.
What kind of easy function?
Yeah.
Okay, got it.
In the
Yeah, if you want to do joins across tables, SQL becomes a benefit rather than a con.
Advanced user. It's very strict.
Any more questions?
Okay,
Yeah.
what is this wide event?
So wide event just means like we're just gonna put all of our stuff in one table, like all of our events, like things that we care about, whether it's a trace or a log or whatever, we're gonna put it all in one table with as many columns as we need in order to describe it.
And so, but you guys are storing this in the database. Now, I had a company had a PayFast. They basically stored all their logs in Postgres, right?
Yep.
And they left it there, and then you had to roll them off, and it was like 8 years or 10 years worth of logs sitting
That
there.
sounds expensive.
It was. So I fixed it. But basically, we ended up having them just put Parquet directly into S3, and then they would just do an OpenSearch search against that with Glue. And so it actually cut it down to $17 a month
Yep.
versus like thousands of dollars. Anyway, so that,
Parquet is awesome.
so does, oh yeah, Parquet is amazing. I've used it at ZeniMax for certain things too, and it's basically a 7-bit binary stream at the end of the day when you actually have a bunch of those going through, right? Like if you compressed it correctly. So I think it's what, 6-to-1, 4-to-1, 12-to-1, something like that. With some of them, some of the different compression
Hmm.
algorithms you can go against. ZSTP is actually the one with the best, I think.
Yep.
You get anywhere from 4-to-1 to 12-to-1 with that, which is wild, especially if you're glaciering it, because then you're like not paying anything for it, right? Um, but so does ClickHouse have built-in stuff that does anything like that? That instead of like sending it, instead of keeping a copy of the data, like
Yep.
keeping flash data, hot data, that's cool. But does it send? Do you have like an option to send like a certain time period back to?
That's what we're actively building right now. What we have already is the read path. So if you're getting the Parquet data into S3 through some other tool, like Flink or whatever, like from your Postgres, we now have through Project Antalya that you can read that data and it will appear to be a ClickHouse table to ClickHouse.
Well, really, what I wanted to do is, and what I want when I build it is, I want the application to just dump everything in S3, and
Yep.
then everything else gets read, unless it's super urgent, critical data. Then that gets pushed over. Then the application at the application level. That's how
Yeah,
it's done.
you could do that. You could do that today with Project Antalya. You should check it out.
Okay, cool.
Yeah.
All right. Yeah, awesome. I'll check you guys out.
Yeah.
So, like Postgres is SQL and the Cassandra is a NoSQL database, right?
Yes, that's
So
correct.
there is the problem why we go for SQL is we compromise on some of the ACID principles. So like the consistency will be eventual consistency with Cassandra.
Yeah.
So when we, take this particular use case for logging tracing. So when it is distributed, so we have the problem of storing. The response time will be fast, or it may not be consistent with the log, and the timing may change, right, for the commit.
Yes. Yeah. Yeah.
How we handle that? How Cassandra is looking like that?
I would argue that in observability, that's kind of okay, right? Because you're not trying to necessarily compare that value to an exact value. You're kind of more looking at like, right? Like if your data is off by a little bit, it's not going to really throw off your analysis, especially if you're looking at like very, very real-time things. So yeah, like most observability tools are definitely going to have like a delay of anywhere from a minute to a few minutes before the data really becomes consistent.
Eventually observable.
Yeah, eventually observable. And they will tell you that it's a real-time tool, but real-time is, right, fuzzy.
And also don't use accounting.
Yeah. Okay, we're at time. Thank you so much. And I have stickers.